So 52 is the integral from 1/2 to 1 over the square root of 2 from 4 over the square root of 1 minus x squared dx. Awesome. Very good pick. Good. So first of all, I have to make sure that this function is continuous on the given interval. So I have 1 minus x squared greater than 0. And multiply both sides by -1, x squared minus 1 less than 0, x plus 1, x minus 1 less than 0. So these, you can check, the interval is -1, 1. These are numbers between -1 and 1. This is 0.5, and this is a little bit more than 0.5, but not beyond 1. So it is continuous. So now I have to think in terms of, so 4 goes outside, of course, does not belong there. I have to find the antiderivative, the function whose derivative is 1 over the square root of 1 minus x squared, and then evaluate it from 1/2 to 1 over the square root of 2, or the square root of 2 over 2, which is the same thing. So now the whole problem reduces to finding the function whose derivative is 1 over the square root of 1 minus x squared. Do we remember a function whose derivative is 1 over the square root of 1 minus x squared? A function whose derivative is 1 over the square root of 1 minus x squared.
Square root of 1 minus x squared. Yeah.
Arc sine prime is 1 over the square root of 1 minus x squared. Arc cosine prime is -1 over the square root of 1 minus x squared. Okay, so now from here, I'm going over all this, which I'm on page 10. So then I have 4 outside. Arc sine of the square root of 2 over 2 minus arc sine of 1/2. So 4. Anyone remembers which angle has sine the square root of 2 over 2, and which angle has sine 1 over 2? Anyone? So no one remembers which angle has sine the square root of 2 over 2? I refuse to believe that. Which angle has sine the square root of 2 over 2?
35 degrees.
Very good. And which angle has sine 1/2? And we have to write it in radians.
Pi over 6.
That's it. So the least common denominator is 12. This one needs a 3 and this one needs a 2. 3 pi minus 2 pi is pi. I'll simplify and I get pi over 3. That's how we use FTC to determine definite integrals. Anything else you would like to pick? Anything? let's work on another problem.
Can we work on 46?
Yes, 46. So in 46, we have the integral from 1 through 18 from the square root of 3 over z dz. So of course, if the function is in z, then we have dz. If the function is in x, we have dx. If the function is in w, we have dw. Perfect. So always remember, patience, simplify as much as possible. So I see that this integral from, of course, z cannot be 0, it has to be a positive number. So yes, this is continuous. I checked between 1 and 18. It's not continuous everywhere. I don't care. I only care if it's continuous on the closed interval 1, 18. So 1 to 18, then I know that this is something like this. I see a constant, I get rid of it. I change this into z to negative 1/2. Ah. And now, after all this, it becomes easy. So I have z to negative 1/2 plus 1, which is 1/2, and I have to divide by that result from 1 through 18. So I flip this, so it's 2 the square root of 3, and it has to stay in front. Open, plug in 18, and subtract when I plug in 1. The square root of 1 is 1. So this is 2 the square root of 3, and this will be the square root of 18, which is 9 and 2. So this is 3 the square root of 2 minus 1. I wouldn't do anything else to it. Good pick. This is another example in which if I just jump and try to do something else before I simplify it, it's not going to work at all. Perfect. Did we get the picture on how to apply FTC? Do you feel like choosing? Let's go again. We're going to have more examples, of course. Oh, you know what? I want to choose something myself. I want to choose 39. So 39, it's the integral from 1 to 3 from 2x plus 1 over x dx. Is this function continuous? Because if it's not continuous on 1 comma 3, closed interval, then FTC is not applicable and I'm wasting my time. Is it?
Yes.
Yes, perfect. So then all I have to do is find the antiderivative and evaluate it from 1 to 3. Which function prime is 2x? You already told me a few minutes ago, it's x squared plus. Which function prime is 1 over x? Say it again.
Natural log of x.
Excellent, very good. And we have to write the absolute value. We discussed that some time ago, that this derivative is 1 over x. Okay, so now I will plug in 3. You can say, but it's you're telling us this, but this is redundant because I don't need the absolute value on 1, 3. True, but initially I have to write it. And then I'll drop it because it's 1 to 3. So the answer will be 9 plus natural log 3, and of course no absolute value, minus when I plug in 1, minus when I plug in 1, but that's 0. So the answer will be 8 plus natural log 3. Okay, this is not the last chance. We'll have other examples. Let's look at also 53. And then we're going to go back to Fundamental Theorem of Calculus Part 1. So in 53, we're asked to find the integral from 0 to pi from f of x dx. And we are given f of x as a piecewise defined function sine x between 0 and pi over 2, and cosine x between pi over 2 and pi. Okay, fine. So the integral from f of x dx, which is a piecewise defined function, is between 0 and pi. 0 to pi over 2, and pi over 2 to pi, and pi over 2 is between 0 and pi. Can anyone tell us, and here's my hint. This is one of the properties that we looked at, one of those 10 properties. Can anyone tell us how to write it? Anyone wants to give it a shot? Anyone?
Is it sine x, like is it 0 and then pi over 2?
Yes.
And then the other one's just pi over 2 and pi.
Excellent. Awesome.
Do we write sine x?
Very good.
Sure. And then cos x?
That's it. That's it. So which function prime is sine x?
Cos x.
Very good, but negative.
Yeah.
Very good.
Right.
Plus, because cosine prime is negative, sine with minus will give us the sine.
Oh yeah, I'm thinking the other way around. Yeah.
Yes,
and then
I know.
One's
Yep, I know sometimes it's confusing. So which
sine
function?
x.
Yes, indeed. Good. So now we have to plug in pi over 2. But when I plug in pi over 2, I get 0. Okay? So minus 0, or minus, outside. Leave it outside. I plug in pi over 2, I get 0. Minus when I plug in 0, and I get 1.
0. Or 1.
Cosine 0, yep. Plus sine pi, 0. Minus when I plug in pi over 2, which is 1. So positive 1, minus 1, it appears that that's 0. Good. So now let's talk about FTC part 1. So a few minutes ago, I said in a minute. So part 2 teaches us how to find the definite integral. How? Finding the antiderivative, evaluating it from a to b, plugging in b, subtract when I plug in a. So this was part 2. Now let's talk about part 1. What does part 1 teach us? So I would go to the next page. So FTC part 1 teaches us that differentiation and integration are inverse operations. It teaches us that differentiation and integration are inverse operations. Okay, so let's illustrate this and then draw a conclusion together. Again, our best friend, and the function f of x, and the area, of course. So this is the area, the exact area, the definite integral from a to b from f of x dx. Okay, that we know. Now I'm going to change the notation a little bit and graph the same thing again. I'm going to denote this by t. Who cares? It's not important. But it is important for what I'm trying to explain. I do have still a and b. And this is still the same thing. It's the area between a and b from f of t dt, the whole thing. So the area, the integral from a to b from f of t dt. Done. However, let's say I have x. And x is a number that goes from a to b. So if I have the interval 1, 10, x can be 1, can be 1.1, can be 2, can be 3, can be anything here between a and b. So for x in this particular position, can anyone tell us what is this and how do I write it? For x in any position, let's say it's right here now. I can make it here. And then I get this area. I can make it here, I can make it here, anywhere. Imagine that x is anywhere between a and b, let's say in this position or any position. And can anyone explain this piece for us? How do I write that? As an area, of course. Give it a shot based on what we just studied today. We know how to express the entire area, right? From a to b, from f of t dt. But what if I want to express just this area? How do I do it?
A to x.
Of course, awesome. Yes, but that's what it is. From f of t dt. Excellent. That's all I needed. So now, imagine this is 1 and 10. If x is 1, you will say the answer is 0. If x is 2, you will say it will be some number, right? So the integral from 1 to 2 from f of t dt will be a number. Then if x is now 3, the integral from 1 to 3 from f of t dt will be another number. If x is whatever, and I continue anywhere between a and b, between 1 and 10 in my silly example. So can anyone tell us what this represents? It's not a number. Is a number if x is this, another number if x is the next, another number if x is the next, another number and another number and another number. This is not a unique number. For any x, I get a new number. So what did I create here? What is this? If the input changes from 1 to 10 and the output is always different, what am I creating here? What is this?
Function.
Excellent. Brilliant. This is a function. This is a function of x given as an integral. It's an integral. Right here, it's an integral. But it's not a number. It's a function because it depends on x. X can go from 1 to 10 or a to b. So I can say that this is basically a of x. Here I couldn't because this is a number. This is just one number, whatever it is. It's the entire area between a and b. Because this is a constant, this is a constant. The answer would be a number. But now, if the upper limit of the integration, of the integral, is x, then this is no longer a number, but a function of x, fancy, in a fancy way, given as an integral. Okay, Fine. So what? Well, we're going to denote that. It's not that it's important right now, but for the illustration of the theorem, I'm going to call this g of x. Okay, so now we know how this comes about. How? By saying that x is a number between a and b, and replacing the upper limit is x. When the upper limit is x, this becomes a function of x. Okay, so now where are you going with this? Part 1 teaches us that differentiation and integration are inverse operations. Okay, show me. Okay, so once we have a function in the form of an integral, only in this case, and we differentiate both sides as we did with implicit differentiation, etc., etc., the left-hand side is g prime. Now the right-hand side, when I differentiate an integral, I get the function back. When I differentiate an integral, this symbol disappears, this symbol disappears because they are together. So when I differentiate an integral, this goes away, this goes away. And what do I get back? I get the function of this. I cannot differentiate if I have b, because that will be 0. It's a number when I differentiate it, but this is a function. So this is what FTC Part 1 is teaching us, that if you differentiate an integral, you get the function back. And this is what I said at the beginning of the class today. If I differentiate this side, whatever it is, it could be in a form of a function or in whatever it is. If I differentiate this, I have to differentiate the other side. And when I differentiate this, the integral symbol, the dx, go away, and I recover the function. So I didn't tell you what I did here. I only said for indefinite integrals, we can always check. If I differentiate the left-hand side, I get f of x. If I differentiate the right-hand side, I get f of x plus c prime, which has to equal f of x. Otherwise, these two are not correct. I mean, this is not that. So how do I apply this concept? But notice that the upper limit is x. But what if I have a function g of x as the integral from a to sine x? And now I don't have x. I have a function of x from f of t dt. And by the way,